Okay, thank you for the introduction and good morning everyone. I'm Vittorio Buccheri and I will talk about tunable nonlinearity in superconducting resonator, hosting aluminum-caped indium arsenide nanowires. Just a brief presentation. I work at Chalmers University of Technology, where I am a PhD student in the group of Simone Gasparinetti. Our group is called 22Q Lab, and we focus on quantum computing with bosonic modes, quantum thermodynamics, and quantum enabling technologies, which is also the topic of this talk. So I want to talk about nonlinear resonator. In order to make a nonlinear resonator, we need a nonlinear element, and this schematics shows that the Josephson junction is the simplest way to implement such an element. It also shows that we can arrange one or more junctions in different nonlinear geometries, such as squids or snails. Why is this useful? Well, because with such kind of device, we can obtain, we can apply this device in several applications, like parametric amplification, nonlinear coupling, and bosonic mode quantum computing. Now, probably the tunnel junction is the most common type of weak link, but as you know, there are other types. And as suggested by the final part of my title, I want to focus on semiconducting Josephson junctions in indium arsenide nanowire. The advantage of semiconducting superconducting hybrid devices is that we gain an additional experimental knob, which is the gate tunability. So let me now present our device. Here you can see a false-colored SEM picture of the device. In the inset, there is a schematic of the section of the nanowire. The nanowire is an hexagon. It has a core of indium arsenide, and 3 out of 6 facets of the core are covered with aluminum. So we can deposit the nanowire in our chip. We can remove part of the aluminum, like here and here, to create the junctions. And then we can deposit the gate to control the junction, and then the ohmics to embed the nanowire in the resonator structure. This is an optical picture of the full device. I will not get into the details of the resonator, but if you're interested, we can discuss later, or you can check out these publications where the same geometry has been used. Now, you may have been noticed that this is a 2-junctions device, but in the rest of my presentation, I will focus on a simpler case. So I will pinch off one of the junction so that effectively I will have a single junction device. And this is the model. So basically, you can see we have our weak link. It is coupled to the resonator via an RF squid configuration, and the experimental knobs are the gate voltage that controls the junction, then the current that flows in a flux line close to the squid, and then the signal, the probe and the pump signals that we can send through the transmission line coupled to the resonator. And now the question is, how does the weak link affect the resonator? The first thing I want to discuss is the frequency shift. In these color plots, you can see the reflection coefficient as a function of the probe frequency and the flux line for 3 increasing values of gate voltage, 1, 2, and 3. Starting from the top plot, you see that the resonator trace is oscillating around 6.76 gigahertz. This oscillation increases when we increase the gate, but then eventually, upon further increase of the gate, the frequency shift pattern changes and we find an anti-crossing. We can explain this data by considering the Andreev bound state physics. In particular, in the simplest case, we can consider that we have an Andreev bound state in our weak link. So an Andreev bound state is a 2-level system, and this is potential, so it depends on the superconducting gap of the leads. Then it depends on the tau, which is the transparency of the junction that we can control with the gate. And then it depends on phi, which is the phase across the junction that we can control with our flux line. So if we plot the transmission frequency of this 2-level system, you can follow here the first line, the blue pattern. We see that such a frequency is very close to the superconducting gap at phase equal 0 and 2 pi, and then it reaches its minimum at phase equal pi. Now, if we increase the voltage, we are basically increasing the transparency, and the consequence is that we are pushing this minimum lower and lower in frequency, so that it gets closer to the resonator. That's why the oscillation of the frequency increase, because the coupling with the non-layer bound state is increasing, and eventually, when the level crosses the resonator line, we find the anti-crossing. So basically, we can plug in this potential in the Hamiltonian, describing this system, and we can see that actually we have a good qualitatively agreement of with our data, even in this simple case model with a single Andreev bound state. Now, when we plug this potential in the Hamiltonian, actually the potential will give also some nonlinear elements. So that's what I'm going to discuss now. I will not. Just to notice, you see how the losses of the resonator are changing when the resonator gets closer, when the Andreev bound state gets closer to the resonator, but I will not discuss that in this talk. So the first nonlinearity I want to show you is the Kerr. We can extract the Kerr by plotting the power-induced frequency shift of the resonator as average photon numbers in the cavity. We can fit our data with this expression, and the linear component, capital K, is our Kerr. Here you see the result of the Kerr as a function of the phase, and for the three different values voltage that we are considering, we see that the pattern is more or less reversed to symmetric, let's say, compared to the frequency shift, and we see that we still have some sort of qualitatively agreement with our simple model. I want to focus actually in pointing out how well we can tune the Kerr in this device. If I show you a zoom of our data close to zero Kerr, we see that actually we can move the Kerr from positive to negative values, but using the phase and the gate. And this, this is very useful for several kind of application where, for example, we want to nullify the Kerr. The other nonlinearity I want to discuss is the three-way mixing. On the left plot, you can see a comparison between pump on and pump off measurement. In gray, you see the pump off at low probe frequency, where we can see just the trace of the resonator. When we turn on the pump, we have an amplification process that increases our signal. If I plot the gain as a function of the pump frequency, we see that the gain is maximum around when the pump frequency is twice the frequency of the resonator, and this is the signature of a three-way mixing. Even in this case, I can show you that we are able to tune these nonlinearities, both changing the phase and the voltage. Again, we have a weak qualitatively agreement with our simple model, where in this case we can consider an interplay between the third order nonlinearity in the Hamiltonian and the Kerr. So basically we see that our peaks here are consistent with the peaks of the third order nonlinearity, and when the Kerr when the three-way mixing disappear is where basically we have a strong interference with the Kerr. To the best of my knowledge, this is the first observation of three-way mixing in superconducting semiconducting hybrid system, well, at least in this kind of device, while in other case, four-way mixing has been reported. So the conclusion, I show you how semiconducting junction is affecting the properties of a resonator. I show you how changes the frequency shift. I show you how we can tune both the Kerr and the three-way mixing with the phase and the gate. So future direction, of course, would be to improve our model, to try to see if we can get a better tunability of the nonlinearities by using both junctions, and eventually try to integrate this system in some device where a tunability of Kerr and three-way mixing, which means also even an odd term of the nonlinearities of the Hamiltonian, can be useful. So thank you for your attention, and please get in touch with our group if you want to know more about our work.
Okay. 2 questions.
Hi, thank you for the talk. I didn't get When you explain the anti-crossing that you see, you only use one of the undirect bound states, or you have to use both of them to explain it, like the ground and the excited one?
Well, basically, these are the two branches of the undirect bound state. This is the ground, this is the excited, and the frequency of the undirect bound state is the excitation between these two levels. So basically, in the bottom plot, I'm plotting the difference between these two curves. So this is the frequency of the undirect bound state. And this is basically, this is what we see if we do a two-tone spectroscopy of the system. I mean, if we do a two-tone spectroscopy close to phase equal pi, we indeed see only one level for the frequency range we can see. But probably one of the reasons why the model is doesn't fit quantitatively the data is that we should include probably higher other kind of level, or maybe the influence of the continuum. So for sure, considering a single level is only an approximation. Also because the junction is around 200 nanometers, so it's not exactly like a point contact. I mean.
But if you take the transparency that you got from the anti-crossings, does it match the inductive, away from half plus, the inductive curvature that you get in
Yeah, no, actually these values are the values that I get from the two-tone spectroscopy that matches the level close to the phase equal pi.
And you plot it against the resonator frequency, does it match?
Well, if you see here, it matches only qualitatively.
Thank you for the speaker. And next